Today, we can begin a new chapter, that is Thermodynamics, chapter 6, Thermodynamics. In a chemical reaction, there are a lot of energy changes. When we consider a chemical reaction, it is associated with a lot of energy changes. So thermodynamics deals with the energy changes associated with a system. So what is a system? System can be defined as the part of universe which is under investigation. The part of universe which is under investigation. For example, if we are conducting an experiment in a test tube, we will take reagents inside that test tube. That mixture of reagents, that is system, not the test tube completely. Only the portion of the test tube carrying the reagent, that is the system. And the rest of the universe is known as surroundings. There are three types of systems. Open system which can exchange energy and matter with the surroundings. System which can exchange energy and matter with the surroundings. That is open system. For example, water taken in an open vessel, water will evaporate. Transfer of matter. For the evaporation, it will take energy from the surroundings, heat energy from the surroundings, exchange of energy. So exchange of energy and matter with the surroundings. That is an open system. Now closed system. In closed system, exchange of energy is possible, but matter is not possible. System which can exchange energy but cannot exchange matter with the surroundings. That is closed system. System which can exchange energy only with the surroundings. Now the third one is isolated system. Closed system, an example is water kept in a closed vessel. It will take energy from the surroundings, but the matter, that means water cannot move to the surroundings because the system is closed. A closed system will not allow the movement of matter to the surroundings. Isolated system in which exchange of matter and energy are not possible. System which cannot exchange energy and matter with the surroundings. That is an isolated system. We cannot give an exact example for an isolated system. We can consider a vacuum flask as an isolated system, almost an isolated system, not completely an isolated system. Okay, now state of a system. What is meant by state of a system? If we want to understand a system, we have to mention certain things. What is its temperature? What is its pressure? What is its volume? Such certain things are required to understand the state of a system. The description of the system in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure, volume, and temperature, as well as the composition of the system is known as state of the system. So state of the system means we have a clear idea about its pressure, temperature, volume, composition, etc. That is state of a system. When this state will change, When you change any of this one, when you change pressure, state of the system will change. When you change temperature, state of the system will change. When you change volume, state of the system will change. Or if there is any change in composition, state of the system will change. Then what is meant by state variables or state functions? State variables or state functions. Variables whose values depend only on the state of the system and not on the path of the change. Only on the initial state and final state, not on the path of the change. That is state functions or state variables that depend only on the initial state and final state, whatever may be the path followed. The state functions are independent of the path. Depends only on the initial state and final state. For example, pressure, temperature, volume, energy, initial value and final value. We are only considering the initial value and final value. The difference is the difference in temperature, difference in volume, difference in pressure, or difference in energy. Only the initial and final states are considered. They are state variables or state functions. What is meant by path function? The functions which depends on the path through which the change is happening. That is path function. An example is work. Work is a suitable example. That is depending on the path through which the change is happening. Next one, internal energy. Internal energy is a state function. Already we mentioned the energy is a state function. Internal energy, a particular term that we are using in thermodynamics to represent the total energy of the system. So internal energy is a quantity which represents the total energy of the system, which is the sum of chemical, electrical, mechanical, vibrational, rotational, or any other type of energy of the system represented as U. There are different types of energies, and internal energy is the sum of all these types of energy associated with the system. That is internal energy. That is represented as U. U is using to represent internal energy. Internal energy may change when heat passes into or out of the system. If we supply heat energy to the system, there is a chance to change internal energy. Or if the heat energy is flowing out of the system, then there is a change. We can expect a change in internal energy. When work is done on the system or by the system, when we do a work on the system, there is a chance to change internal energy. Or when the system is doing work, there is a chance to change internal energy. And the third case, matter enters or leaves the system. When matter enters, there is a chance to change the internal energy because the content is increasing. When matter leaves the system, there is a chance to change the internal energy. The reason the content is decreasing. Change in internal energy, that is represented as delta U, and that is equal to internal energy of final state minus internal energy of initial state. That is delta U, change in internal energy. Or different types of thermodynamic processes. A process is the change of state of a system. Thermodynamic process is the process of change of a system from one state to another. They are mainly classified into four. The first one, isothermal process. Isothermal, constant temperature. Isothermal process means constant temperature process. It is a process at constant temperature in which the system can change energy with the surroundings, exchange energy with the surroundings. It is a process at constant temperature in which the system can exchange energy with the surroundings. So the walls of the container is conducting walls. Isothermal process include exchange of energy with the surroundings. If you want to keep the temperature of the system constant, either it has to absorb heat energy from the surroundings or it has to remove heat energy to the surroundings. Then only it can keep its temperature constant. So the walls of the container should be conducting walls. The second one is adiabatic process. In adiabatic process, there is no transfer of heat between the system and surroundings. No transfer of heat between the system and surroundings. Usually, the adiabatic processes are sudden changes. Adiabatic process are sudden changes. It will not get enough time to accept energy from the surroundings, or it will not get time to give energy to the surroundings. Usually, there are sudden changes. So in adiabatic process, there is no transfer of heat between the system and surroundings. So the wall separating the system and surrounding is called an adiabatic wall. Another process is isochoric process. It is a process at a constant volume condition. At a constant volume condition. Isobaric means constant pressure process. Isobaric process, constant pressure process. A process at a constant pressure without any change in pressure. Now another term, work. Already we mentioned internal energy can change when work is done on the system or done by the system. When work is done on the system, it is a gain for the system. Gain represented using plus, positive sign. By convention of IUPAC in chemical thermodynamics, the positive sign expresses that W is positive when work is done on the system, and the internal energy of the system increases if the process is adiabatic. When the work is done on the system, the internal energy increases if the process is adiabatic. That means no exchange of heat energy with the surroundings. If it is not giving energy to the surroundings, we can expect an increase in internal energy when work is done on the system. And when work is done by the system, that is represented using a negative sign, and there is a chance to reduce the internal energy. One condition is there, if the process is adiabatic, that means if it is not taking energy from the surroundings. There is another term, heat energy, Q, represented using the letter Q, heat energy. Heat energy also can change the internal energy. So if there is a gain, that means heat is supplied to the system represented using a positive sign, and the heat is taken away from the system, that is represented using a negative sign. By conventions of IUPAC in chemical thermodynamics, the Q is positive when heat is transferred from the surroundings to the system, and the internal energy of the system increases. There is a condition There should not be any work done by the system. If the system is doing work, we cannot expect a change in internal energy. Otherwise, if we supply heat energies to the system, surely the internal energy of the system is increasing. Q is negative when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. There also a condition. There should not be any work is done on the system. If there is no work is done on the system, when temperature is taken out of the system, surely the internal energy of the system will decrease. So these two, heat and work, these two can affect internal energy of a system. Heat or work can affect the internal energy of a system. So we have to consider these two together. So let us consider the general case in which a change of state is brought about both by doing a work and by transfer of heat. Then we can write the change in internal energy delta U is equal to Q plus W. Delta U change in internal energy, Q heat energy, W work done. And this equation delta U is equal to Q plus W is mathematical statement of the first law of thermodynamics. It can be stated as energy can neither be created nor be destroyed. First law of thermodynamics stated as energy can neither be created nor be destroyed. And its mathematical expression delta U is equal to Q plus W. Delta U is equal to Q plus W. It is first law of thermodynamics. In order to understand it properly, we can solve some problems here. Express the change in internal energy of a system when, what you have to find out? Delta U. Express the change in internal energy of a system when, one, no heat is absorbed by the system from the surroundings. No heat is absorbed by the system from the surroundings. But work, W is done on the system. Work is done on the system means W is positive. Q is 0. No work is, no heat is supplied to the system, or no heat is taken from the system. If there is no transfer of heat between system and surroundings, the process will be adiabatic, isn't it? What type of wall does the system have? We can easily say adiabatic wall. So what is first law of thermodynamics? Delta U is equal to Q plus W, and here Q is 0. Q is 0. Work is done on the system. W is positive. So delta U is equal to W. Delta U is equal to W. Here Q is equal to 0. Delta U, Q plus W. That means 0 plus W. Since it is adiabatic, W adiabatic. So it is, the wall is adiabatic. Second one, no work is done on the system. The common question is you have to find out the change in internal energy. And in the second case, no work is done on the system. There is no work. W is equal to 0. But Q amount of heat is taken out from the system. Q amount of heat is taken out from the system. And means Q is negative. So delta U is equal to Q plus W minus Q plus 0. Delta U is equal to minus Q. And here heat is transferred. So the walls should be thermally conducting. The wall should be thermally conducting. Delta U is equal to minus Q. And the system has thermally conducting walls. And the last one, W amount of work is done by the system. W is positive. And Q amount of heat is supplied to the system. W is negative. W amount of work is done by the system means W is negative. And Q amount of heat is supplied to the system. Q is positive, supplied to, so positive. So here it is, what type of system would it be? There is nothing about the transfer of matter with the surroundings, but there is transfer of energy with the surroundings. So we can say it is a closed system, and delta U is equal to Q plus W. Q is positive and W is negative, so Q minus W. Q minus W. Delta U is equal to Q minus, and the system is closed system. If you want to see more problems related to first law of thermodynamics, you should understand the work done in the case of a reversible process and an irreversible process. What is meant by a reversible process? What is meant by an irreversible process? A reversible process that will take place very slowly by maintaining an equilibrium in each step. You should keep an equilibrium in each step of the process. Means at any time it can be reversed. In thermodynamics, this reversible process and irreversible process are important. Usually, the processes are irreversible, but there is chance for reversible process, and that process will take place infinitesimally slowly, very, very slowly. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. At any time it can be reversed. A reversible process proceeds infinitely slowly by a series of equilibrium states. So what is a reversible process? You have to remember only this part. A reversible process proceeds infinitely slowly by a series of equilibrium states, such that system and the surroundings are always in near equilibrium with each other. To understand it, a suitable example is given in your textbook. Consider a gas taken in a cylinder and it is closed with a piston, cylindrical vessel, and it is closed with a piston. And on this piston, about 1 kilogram finely powdered dry soil is placed. Above this piston, 1 kilogram of finely powdered dry soil is placed on this piston. Now, because of the weight of the soil, the gas will be slightly compressed. Now, the piston is not moving back. That is in an equilibrium state. That means internal pressure and external pressure are equal. So there is no expansion. Now you remove one fine particle of soil from it. Then what happens? External pressure slightly decreases. Slightly means we cannot imagine it, such a small decrease. Then internal pressure will be more and a slight expansion. And it expands, internal pressure decreases, and again an equilibrium state will reach. Then you remove another small particle, another small fine particle, again expansion. equilibrium. Remove one more small fine particle. Again expansion, equilibrium. Remove one more small fine particle. Again equilibrium, expansion and equilibrium. Again remove one more fine particle, expansion, equilibrium. Remove one more fine particle, expansion, equilibrium. So that process will proceed very slowly. That is a reversible process. That is a reversible process. All other processes are irreversible process. Sudden expansions are irreversible process. And now we have to compare the work done in the case of a reversible process and irreversible process. First, we can see a irreversible process. Pressure volume work in an irreversible process. In the case of expansion, work is done by the system. So simply we can write it as W is equal to minus P delta V. Delta V means change in volume minus P delta V W. In the case of expansion, work is done by the system. So minus P external, work is done against external pressure. So minus P external delta V, work is done by the system. That will be negative. It is the expression to find out work done in the case of an irreversible expansion. And if it is irreversible compression, the opposite, W is equal to P delta V. Here we can plot a graph between pressure and volume and the area. It is the change in pressure and it is the change in volume. So P into delta V, that will give you the area or work done by the system. External pressure, if we are starting from 0 here, it is the external pressure. This difference means it is the external pressure into delta V, change in volume. P external into delta V. Here it is represent compression. It is the initial volume, it is the final volume. Decrease in volume, compression. So P external into delta. And if it is expansion, W is equal to minus P external into delta V. Now, in the case of reversible expansion, work in an isothermal reversible process, the process is reversible. The process will be isothermal. It is very slow process, infinitely slow process. Therefore, it has enough time to take energy from the surroundings or to give energy to the surroundings, thus it can keep its temperature constant. So that will be an isothermal process. So work done in an isothermal reversible process. So here we can see, here work is against an external pressure. If it is expansion, the case of expansion, volume is increasing, isn't it? Volume is increasing in the case of an external pressure. So work is done against the external pressure. You have to remember the example that we discussed earlier. When you remove a fine particle, what happens? A slight expansion will take place. As the expansion happens, what is the problem? The internal pressure will decrease. The internal pressure will decrease. So in order to compensate, or in order to keep the internal pressure more, we have to remove another particle. Then what happens? A slight expansion. So step by step expansion. When a fine particle is removed, this much expansion happens. And another particle is removed, this much expansion. And another particle is removed, this much expansion. And another particle is removed, this much expansion. So thus the expansion is happening step by step, slowly. And the total expansion, the work done, if you want to find out the work done, you have to find out the total expansion. And if you want to find out the total expansion, you have to integrate the work done in this small expansion for the total volume change from V initial to V final. Then only you will get the total work done. That is given here. We know PV is equal to nRT or P is equal to nRT by V. So P delta V can be represented as nRT by V dV, small change in volume. The first is small change in volume. So work done in isothermal reversible process is equal to minus integral V initial to V final nRT dV by V is equal to minus nRT ln Vf by Vi. When we convert it to the logarithm to the base 10, you have to multiply it to 2.303. So work in the case of reversible expansion is equal to minus 2.303 nRT log Vf by Vi. When we compare the work done in the case of isothermal reversible expansion and irreversible expansion, we can see the work done is slightly more in the case of reversible expansion. Now, I would like to introduce one more term, free expansion. Expansion of a gas in vacuum, that is external pressure is zero, that is known as free expansion. And in the case of free expansion, there is no work. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. So I think we can stop it here and we can discuss the problems in the next class. Okay.